but I
Yeah.
believe that my topic will be less challenging than my name.
Okay, good. Thank
So
you.
let me try to share my screen, and I hope that you can see it. Can you?
Yeah, now we can see it very well.
Excellent. Is my audio also
Yeah,
good?
yeah, all is
Good
perfect. So
enough?
you can start.
All right. I'm really happy to have the previous speakers today who spent some time explaining the complexity of the modern instrumentation. And I would like to walk you through the challenges and solutions which MPI provides to our customers. We bring all this measurement instrumentation and integrate them on the wafer-level measurement systems. And this is what I'm going to discuss with you today. Let me start with a short introduction. We talked multiple times about new wireless communication systems, which made a mind-blowing evolution over the last 4 decades. So everything started with the first simple 1G, 2G systems, which were focused just on delivering the speech to the customers. Later, we added services like internet and some other digital services with the introduction of this 3G. And 4G brought the rise of mobile internet, whereas 5G is currently focusing on machine-to-machine communication and Internet of Things. With the 6G, it is expected that the human and their needs will be in the center once again. And all this evolution wouldn't be possible to do without the progress in microwave measurement techniques, instrumentation, and the software. So let us review what we can do today with the modern microwave instrumentation. So this slide gives just one of example what's possible, what kind of the measurements are possible to achieve today using modern vector network analyzers. This is an example is a Keysight PNAX system with the frequency extender hertz. Using the system, you can do broadband measurements in the frequency range from 90 hertz up to 120 gigahertz. And with outstanding accuracy, dynamic range of the measurement, speed, calibrated power control, and many other features. We call the systems like a software-defined instrumentation. Having just a vector network analyzer, you can also do a lot of other types of the measurements. This instrument has an integrated elements of the spectrum analysis, noise figure analysis, signal generators, pulse generators, and so on. And we can perform large signal, non-linear characterization, time-domain waveforms, modulated waveforms, millimeter wave vector load pull system, and many others. As an example, you can see an integration of such system with the focus microwave and PNS tuners on MPI system, where we can do large signal characterization up to 110 gigahertz. So the complexity of the measurements that we can do today at the wafer level, is enormous. Another example is how we can configure such a system for doing differential measurements, which can be split into different frequency bands like baseband from almost 0 up to 67 gigahertz, and at its full speed, full sweep, DC to 120 gigahertz with the full differential characterization of modern integrated circuits. And these type of the measurements can be done at the fully shielded environment with AMI and light tide protection of the device under test, at the full temperature range of minus 40 up to 175 degrees C, which is limited not by the system itself, but by the RF temperature range. So, and we will get to this point a little bit later today. So also, modern systems enable us doing a very special class of the measurements. And here's just an example how these frequency extenders can be integrated on the thoughts port of the network analyzer, so on the wafer-level system. So you can do multi-port measurements with the full differential drive of your LO. And here's just an example that you can characterize, for instance, the distributed mixer at full frequency range with full required characteristics because we can drive the differential signals at LO up to 110 gigahertz. Previously, this type of the measurements was very challenging to do. Only very limited type of the parameters can be characterized because engineers had to use the magic T and shifter to adjust the frequency of the differential drive for LO. Another class of the instrument was introduced at RFTech 94th conference by Martins and Roberts from Anritsu. And this is the broadband signal sweep system based on vector star from Anritsu, which provides the measurements from 70 kilohertz up to 226 gigahertz, and the system is specified up to 120 gigahertz. This is the whole new domain of the measurement for two different types of engineers. Using this system, modeling engineers can qualify and verify device model parameters, and as well as the final product, like integrated circuits, can be characterized in one sweep at the full frequency range. An important and a challenging part of the system is the interfacing with the RF probe. It's not only enough to have the vector network analyzer, which can generate such outstanding frequency range signal. We also need to deliver the signal to the device under test. So we need a probe. And interfacing with such an instrument became possible after development of a special interface. This is kind of a quasi-coaxial connector. It's a proprietary interface developed at Anritsu, which combines two solutions. This is like a coaxial traditional interface with the 0.6 millimeter connector embedded into the WG387 waveguide flange. So the frequency extender of the vector network analyzer has the female part of such an interface, in RF probe developed by MPI engineers as a male interface. So these two parts can be attached to each other. So if required, system can be reconfigured using other probe configurations, for instance, different pitch, or if probe is damaged, the probe can ship to MPI for using quick repairment process. This is not enough. This system also can easily be scaled for doing a differential measurements. So in this case, we can integrate two frequency extenders just at one side of the system, of the probe system, and the differential probe, also developed by MPI engineers, can be attached to these two frequency extenders, so the integrated circuit can be tested at full differential drive. The frequency range from 70 kilohertz up to 220 gigahertz. And this system is unique, and it opens a new class of the measurements, which previously was not possible to do at all. And I would like to use the chance and share with you the first industry record measurements of a broadband differential driver, millimeter wave driver circuit, which was performed at the University of Ulm in Germany. And this is the group of scientists and researchers from this group, together with Anritsu, MPI, and ATV, people who distribute of MPI in Germany. And this is the first measurement of such a circuit, and we have a picture of this circuit as well. So we collected this data shortly before Christmas 2 years ago. Also, differential characterization and the single-ended characterization, large signal analysis. This is all what we will discuss in our industry workshop. And here's an example of a D-band large signal characterization for 5G, 6G millimeter wave integrated circuits. Also designed and developed in cooperation with Roden Schwartz and Focus Microwave and MPI engineers. And using this chance, I would like to invite you kindly join the industry workshop at IMS 2024 in Washington. This is the Tuesday workshop entitled Optimization of RF Power Amplifiers in the Sub-Targets Frequency Range. Please join us, where we will definitely present, and it will be a great opportunity to discuss all technical aspects related with such challenging systems. So how to do large signal analysis and D-band. Another important parameter is not only acquiring S parameters for large signal RF characteristics of integrated circuits and devices, it's also to do it over the wide temperature range, as we mentioned before. Introducing the temperature parameter in our measurements adds another scale in already a multi-dimensional measurement program. And an MPI, we focused on reducing the challenges associated with over-temperature device and integrated circuit characterization at the wafer level. such challenges is like how to minimize the mechanical drift of the system. When you do long-term measurements and the chuck of the system is sitting in one specific location of the wafer system. So how to minimize this possible mechanical drift of system components. Why this is critical is because if this mechanical drift is minimized or completely eliminated, we have less mechanical distances that has to be compensated by an automated parts of the system. We can collect the data much faster, so we have faster time to data, and the measurement results can be much more accurate. Also, it is essential to minimize the electrical drift in the system. Also happens due to the measurement time and due to the temperature changes. So why this is important to minimize the electrical drift is because we can reduce the number of RF calibration cycles in the system, and we can also increase the measurement accuracy and again, time to data, which is critical. So in MPI, we introduced this solution as a whole total package which contains multiple specific components of a hardware system as well as software implementation, so algorithm and the software itself. We call it automated test at multiple temperatures, ATMT. And it includes innovative solutions for temperature stable hardware parts of the system. Also innovative probe adjustment methods with the software algorithms embedded in Sentio, which is MPI probe control software. We also have a solution how to reduce the time outside of the temperature source, and also how to completely eliminate the temperature changes in the system when we need to calibrate it by introduction of the on-wafer calibration solution supported by Calibria. This is the calibration software developed by MPI engineers. So next slide demonstrates it's a simple implementation of a two-port measurement system with automated test of the multiple temperature solutions. As I mentioned before, it incorporates several hardware and software parts. On the hardware aspect, let me start with RF probes. MPI Titan probe technologies has a unique visibility of the contact point when the probe contacts the device on the test pads. So it's very easy to land the probe and the desired location, not only by inexperienced operator, but also by the software with the very highest repeatability and consistency of the measurement data. Smart carrier, this is another mechanical part of our system, which is integrated with the probe arm, and it minimizes the thermal drift of the thermal expansion of the RF probe over the multiple temperatures. System also enabled with long-term measurement optimized hardware parts such as a probe arm and the probe platen. Also, a system can be configured with programmable positions with specific algorithms of MPI software. We don't need to have programmable positions of every measurement port. For instance, we can do successful automated measurements, a full port system with 3 positioners only. And we have special algorithms for calibration and the probe to pad alignment embedded in Sentio probe control software and Calibria system calibration software. Calibria also supports on-wafer calibration processes. What does that mean, on-wafer calibration? That means that calibration standards can be designed using the same semiconductor process as the device under test and can be incorporated next to the device under test. This is critical for accurate system calibration, accurate measurement results, not only at the wide frequency range, but also over the multiple temperatures. Because the standards are at the same temperature as a device under test, there is no more temperature difference between calibration process and the device measurement processes. So the measurement accuracy drastically increased. Also, because the standard and device under test share the same semiconductor process, the accuracy of the data can be increased drastically, eliminating the need for so-called second-tier calibration methods or pad embedding calibration methods. Different calibration standards can be designed using modern semiconductor processes, such as transmission lines, through standard reflect, as well as the load elements. Not all electrical characteristics of such elements need to be known, which is the huge plus. By using advanced calibration algorithms, such as NIST multi-line TRL, or through match reflect, or through reflect match calibration algorithms developed by MPI, it is very easy to do on-wafer calibration and very accurate calibration, achieve very accurate calibration results in the wide frequency range. And all the features related with this calibration approach and these methods are available from MPI software. Just an example how the graphical user interface looks like when we execute on-wafer calibration process with custom calibration standards. Is the picture where the device under test and the standards next to it can be seen here. The navigator, which enables easy navigation between calibration standards, the calibration standards, which are demonstrated here, embedded on the wafer, and the list of the standards, RF probes, and the vector network analyzer. Everything is designed in one graphical user interface, single-ended operation window. Calibria, the calibration software, manages the location of calibration standards, electrical properties, and the calibration algorithms. And Sentio, probe control software, manages the alignment and the navigation around the calibration standards and probe back alignment and the contact high definition. We recently published an application note which can be found from MPI website technical library, which discusses the challenges and solutions for over-temperature device characterization at wide frequency and temperature range. It's just an extract from it, where we can see the gain of a device under test. This is indium phosphide HBT measured at different bias conditions over multiple temperatures, starting from -40 degrees C and up to 125 degrees C. On a single sweep system from Anritsu integrated on MPI system, where you can see extremely consistent data across the entire frequency range. So the system reconfiguration is not required, and the data are calibrated using on-wafer calibration standards. So what I also would like to emphasize here is that we can even see the device characterization, not operation conditions, which is very high temperature, 125, which was too high for this particular device under test. So even if device doesn't show any gain, we can still acquire accurate measurement results. So that brings me to conclusion of my talk. Progress in instrumentation enabled the development of the next generation highly integrated circuit systems and development of the very accurate device models. Innovative integration solution for wafer-level characterization without compromising the instrument performance exists today. And software and the system automation solutions for over-temperature characterization accelerate time to data for the next generation products for 5G and 6G application research. Thank you very much. And if you have any questions, please find us at IMS. We will be all live present. We will do very interesting measurements at MPI booth. Find us at IMS, and we will be happy to talk to you and answer all your questions there.
Thank you very much, Andrei, for this very nice talk. I think that as we are a little bit late, we can pass directly to our next speaker, who is Mr. Brian Walker. That is a senior radio frequency engineer at Cooper Mountain Technologies, where he helps customers to resolve technical issues and works to develop new solutions for applications of VNA in test and measurements. Brian graduated from the University of New Mexico. He has 40 years